There we go. Good. All right, good. By now afternoon. Today we're going to have a talk on one of the topics that's at the core of research at R&L. Neutron scattering and the facilities used for it, starting in with the initial proposal, I believe it was in May 1944 at the graphite reactor, just a few months after it started up. Today being carried out in steady state at the high flux isotope reactor and in pulse mode at the accelerator-based spallation neutron source. So the specific talk today is on the power upgrade project, the Proton power upgrade project. The goal is to increase the power from basically doubling it from 1.4 to 2.8. That allows more neutrons out of the first target station to enhance science with what exists at spallation neutron source, with proton power left over for a second target station. So our speaker today is Mark Champion. He is the project director, following John Galambos, which many of you may know, of the Proton Power Upgrade Project. John obtained his degrees in electrical engineering at the University of Illinois, Champaign, then moved just a little ways down the road to Fermilab, where he got involved in superconducting radiofrequency technology. He joined the initial SNS project in 2001, working on design, construction, and commissioning of the accelerator complex, then bounced back to Fermilab to lead the superconducting radiofrequency department in the execution of the International Linear Collider R&D and establishing a world-class program at Fermilab. 2012, here we go again, back to Oak Ridge National Laboratory and the spallation neutron source, leading electrical and RF systems, beginning to support the Proton Power Upgrade Project in 2016, and now transitioning first to project manager and now project director. So let's everybody welcome Mark Champion. And just because I know you're going to be mobbed with questions afterwards, here is a token of our appreciation.
That's great. Thank you. So when I went back to Fermilab after we finished the spallation neutron source construction and commissioning, I remember one winter looking out the window of my office and turning to my colleague and saying, "Remind me again, why do people live here?" And so when an opportunity came up, I returned to Oak Ridge, and it also coincided with basically a lack of funding to continue carrying out the ILC R&D program. So it was a good time to transition back to Oak Ridge. And then the Proton Power Upgrade came along, and I've been working on that for the last 7 years or so. And working with John Galambos very closely. He is project director and I as project manager, and that's been a very good relationship. John is a physicist, I'm an engineer, and we balanced each other out very nicely. So before I really dive into this, I'd just like to say that, you know, a project like the Proton Power Upgrade is really a team effort. And there are many people at SNS and elsewhere across Oak Ridge National Lab that have contributed to this success. We're doing very well. We are ahead of schedule, under budget, and meeting technical objectives. So it's a good story. We also had help from colleagues at Jefferson Lab over in Newport News, Virginia, and people from Fermilab. So I was able to go up there a few times and see some old friends who were contributing to this project. So with that, let's dive in. And you're going to advance the slides, correct, Herb? Oh, I am, sorry. Excuse me. Got it. Okay, so I'd like to start with a little bit of a background about the SNS facility. The construction project created a first of a kind facility, and we completed that in the spring of 2006. I'll explain a little bit what I mean by first of a kind in a moment. Since then, we've made a lot of investments in improving the performance of the facility and improving the availability. And we now provide more than 4,000 hours of neutron production per year for the user program. We operate above 90% availability against our schedule, and we routinely operate the facility, the accelerator complex, between 1.4 and 1.7 megawatts. 1.7 because we've brought on the PPU technical equipment in a phased approach. We've expanded the suite of neutron instruments from 3 at project completion to 20 now. And so based on a good track record, our sponsor at DOE, the Office of Basic Energy Sciences, has supported the Proton Power Upgrade Project and the Second Target Station Project, both of which are underway. So I mentioned that there were many firsts involved in the SNS. It was a first of a kind accelerator facility and neutron production facility. One of the big things there is our superconducting linear accelerator. Linear accelerator, we refer to that as a LINAC. And it was the first and remains the only megawatt class superconducting proton accelerator in the world. A number of technologies resulted from the SNS project. I'm going to skip down towards the bottom and mention the liquid mercury target. That was another first. There are 2 facilities in the world that use liquid mercury for spallation sources, SNS here at Oak Ridge and the J-Park facility in Japan. It's a complex system, but it's served us very well. We've had to put a lot of effort into the target module itself. I'll tell you a little bit more about that as we proceed. And then another thing about SNS was that it was a collaboration of 6 US national labs. And that was challenging, but also fun. And ultimately it worked for us. So here's just a overview of the 20 instruments that we have in operation. There is a lot of information available at the neutrons.ornl.gov website if you really want to read about those. But it's a full suite of instruments now. The most recent addition is the Venus instrument, which is presently undergoing commissioning. So now I'll give you a little bit of an overview on what we have at the facility and how it works. We start with a linear accelerator, and that's 2 sections, basically, a normal conducting portion at the low energy end, and then superconducting LINAC at the higher energy. We have an accumulator ring. We accelerate a 1 millisecond long beam in the LINAC, and that beam gets wrapped up in the accumulator ring. It's injected, and there are 1,000 turns. So each mini pulse that comes out of the LINAC is stacked on top of the preceding mini pulse. And in the end, we have a sub-microsecond pulse of protons in the accumulator ring. We extract those 60 times a second and then travel down a beam line to the first target station to our liquid mercury target. And when they hit that target, neutrons fly out in all directions. So we've been operating the facility reliably for several years at 1.4 megawatt proton beam power on target. And just wanted to show you a couple of photographs. These are inside the LINAC tunnel. We've got our drift tube LINAC here. 6 sections that operate at the low energy end of the facility. They accelerate the protons to about 40% the speed of light. They then enter the coupled cavity LINAC. That further accelerates the beam to about 55% the speed of light. And then finally, the protons enter the superconducting LINAC. Prior to the PPU upgrade, we had 23 cryo modules installed in the tunnel, operated at 2 kelvins. 2 different types, one for an intermediate energy range, the so-called medium beta, and then the high beta for the higher energy range. And that just means the cavities themselves that are accelerating the beam are matched for 61% speed of light and 81% speed of light. These are powered with 1 klystron upstairs in a so-called klystron gallery, and the exit energy is 1 GeV, which is approaching 90% the speed of light. So when the SNS was constructed, there were provisions for an upgrade. At the end of the LINAC, there was space in the tunnel for additional cryo modules. We had 9 empty slots. We've used 7 of those as part of PPU. And upstairs, there was a big empty room at the end of the Klystron gallery where we could install more RF systems. The accumulator ring and the transport lines into and out of that were basically ready for 1.3 GeV from day one. So what we're doing is doubling power capability of the Spallation neutron source from 1.4 to 2.8 megawatts by increasing the beam energy 30%, going from 1 GeV to 1.3 GeV, and by increasing the beam current by about 50%. And as a result of this, we'll be able to provide 2 megawatts of beam to the first target station, and balance of power will go to the second target station when it's completed. And you can see in the areas that are circled in blue, the areas that are affected by the upgrade, the LINAC itself, the accumulator ring, and then the first target station. And over here to the right is where we will construct the second target station in the future. So we have a science case, and in fact, I brought a copy if anybody wants to look at this. It's also available online by the links that are here at the bottom of the page. Basically, we're increasing the flux of neutrons coming off of the target by increasing the power that we deposit on the target. And this increases the rate of doing experiments. So it should accelerate the pace of scientific discovery. It also will make possible experiments that are currently not feasible or routine. This is all based on having more neutron flow, a higher neutron flux. We can do time resolved in situ measurements where we're actually watching reactions as they occur. We can do experiments on smaller or less concentrated samples. And that ties into the last point, the more extreme environmental conditions under high pressure or high magnetic fields, high temperature. Smaller samples are easier to handle in those environments. And so having more neutrons enables these experiments that are hard to do now or impossible to do now. Finally, it enables the second target station. I'll tell you a little bit more about that as we go on. So the scope of the upgrade is across the facility in the linear accelerator. Basically, we're doing radio frequency system, new installations and the upgrades of a few existing systems. We have fabricated and installed superconducting cavity cryo modules in the tunnel. There's a little bit of conventional facilities work associated with the Klystron gallery, and we also built a tunnel extension out here to enable connection to the second target station in the future. The accumulator ring saw quite a few upgrades, especially in the injection and extraction regions. I'll come back to that, but that's to accommodate the increased beam energy. And then the target systems themselves. We had to develop a 2 megawatt capable target, and there are supporting systems that had to be modified or added for that target. So starting with the superconducting LINAC, we have added 7 additional cryo modules. That's 28 of the high beta cavities. The cavities themselves are high purity niobium, and the cryo modules were built by Jefferson Lab. We partnered with Jefferson Lab on the original SNS project, so it was kind of natural to go back to them, and some of the same people were still there and supported our upgrade. So with our increased energy of 1.3 GeV, the protons are moving at about 91% the speed of light when they come out of the LINAC. A little bit more on the SRF cavities. You can see in the lower right cavity as it's received from a vendor in Germany. On the left, you can see where we've prepared a cavity for testing. So we mount it on what we call a vertical test stand, and it will be lowered into a dewar and then flooded with liquid helium. And then we'll pull a vacuum on the helium to cool it down to about 2 Kelvin. And this allows us to verify the performance of the cavities before we go to the next step, which is to install the cavities in helium vessels. So these are 4 cavities mounted together in what we call a cavity string. They were installed in the helium vessels at Jefferson Lab. And then, as you'll see here, we insert that cavity string into a vacuum vessel with helium supply and return end cans. But I guess what I really want to point out here is the size of these things. They're about 8 meters long. It's about 24 feet. And we've installed 7 of these in the tunnel. They're operating very well. They all meet requirements. And we have 1 spare that we built as part of the project. So moving on to RF systems. There were 2 main aspects of the RF systems upgrades. We had to install 28 additional RF stations to support the new cryo modules. And there are images here on the right side of the screen showing the klystrons, the high voltage modulator that pulses the klystrons, water system upgrade, low level RF controls. And then we also had to upgrade a few stations in the drift tube LINAC to handle the increased beam current. And so we've got a 3 megawatt klystron here that's increased from 2.5 megawatts. Some modifications to the pulsed high voltage power supply, and also some modifications to the water system that cools that equipment. So all of the RF systems for the new cryo modules are installed and operational. We have 1 of the 3 megawatt klystrons so far that we've put into service, and the others are still pending arrival from the vendor. But we don't need those until we actually get to the second target station era, where we need to provide 2.8 megawatts total. Just a little bit on klystrons. I don't know if you're familiar with klystrons. They're kind of near and dear to my heart because I've worked in the RF area quite a bit over the years, but we have 120 of these that we operate at the SNS to drive the LINAC. They're expensive devices. They have a very high gain, 50 or greater dB, which is a factor of 100,000 in power. And basically, each klystron is a small linear accelerator. There's a cathode that's heated, liberates electrons. It's accelerated by a pulsed high voltage. That beam travels through a series of resonant cavities. On the input cavity, we tickle it with an RF drive signal, and then the particle beam is bunched as it passes through these cavities. And then at the output cavity, you can extract a greatly amplified signal. So for PPU, we installed 28 of these, and they have a cost of about $300,000 each. And then you have all the supporting electronics and systems that you need to operate klystrons. So RF systems were the single biggest expense in this upgrade. Moving to conventional facilities, I mentioned earlier that our klystron gallery was a big empty room when we started. Today it's fully populated, and if you walk along the gallery, you won't be able to tell the new part from the old part, except we have better lighting in the new part. Another aspect of conventional facilities that we carried out over our long outage, finished recently, was the construction of a tunnel extension. So here we are, the accumulator ring is off the screen to the right. The beam travels through here into the first target station. And we built this tunnel extension so that we can easily connect to the second target station later on without shutting down the first target station. We'll be able to keep running while they continue to build tunnel to go over to the second target station. So it saves us a long outage in the future. So the accumulator ring itself, there's been a lot of activity here listed on this slide. The main business has been in the injection region, where we bring in particle beams and it merges with beams already circulating in the ring. And maybe I failed to mention it, but we accelerate H- ions in the LINAC, and those are converted to protons at this injection region. The H- ions travel through a diamond stripping foil. The X-ray electrons are pulled off. Then we have protons circulating, and so we have H- ions and protons merging together in this region. We had to have new magnets to accommodate the increased particle beam energy. We also had to make some changes on the extraction region. We have what we call kicker magnets, that pulse magnets that will fire at the right time to kick the proton beam out of the ring and send it to the target station. We had to do some upgrades there again for the increased beam power. We had to develop a power limiting system to make sure we don't exceed 2 megawatts on the first target station. We're not authorized to go above 2 megawatts on that station. So this is accredited control that it's pretty complex to design and build, and it's in operation now. So here is an image that shows the new magnets that were designed and constructed at Fermilab on the left with the Fermilab team. And then on the right, you can see them installed in the SNS accelerator tunnel. It's a very busy region, a lot of equipment, and during operation, there's some amount of beam loss in this region due to the charge exchange injections scheme. And it becomes somewhat radioactive activated over time. So we had to get it right so that we don't have to work on it in the future. Now I'm going to move to first target station. We have a Mercury target, as was mentioned, and that's in the upper left of the image. But what I wanted to show you here is that we have a system of pipes and a pump, and a heat exchanger that's is constantly circulating the mercury. So the mercury is heated by the proton beam as the proton beam strikes the target. And then we take that mercury one out and get rid of the heat. There's a storage tank down in the basement. So if we have to drain the loop, we can do that. We've got about 18 tons of mercury circulating in the loop. It's 355 gallons. It's kind of amazing to think about, like, where do you get that much mercury? I think it came from Y12. So anyway, let's move on to some more first target station technologies. In the upper left, you can see a new 2 megawatt target that we have a vendor in near Cincinnati that builds targets for us. It's a long build process, approaching a year to build one of these things. So when the proton beam strikes the target, and it strikes here on this end, it's coming in from the right, and it strikes that target. There are two problems. One is there's a pressure pulse in the stainless steel body of the target, and the other is you get cavitation on the inner wall of the target where the mercury is contacting the stainless steel. And this gave us a lot of trouble 10 years ago. We were having targets fail, and we figured out what was going on. We took a cue from our colleagues in Japan, who had demonstrated that the injection of helium bubbles into the mercury was very effective at damping the stress and at mitigating the cavitation. So we've done that. We demonstrated already with our previous generation of targets that it was a great benefit to the operation of the facility. And so for PPU, we wanted to have a 2 megawatt capable target, and we wanted to have high flow helium gas injection capability so that we could feed up to 20 standard liters per minute of helium into the target. The target itself is installed in the target service bay. That's a room where no human may go because it's very activated. So the targets are installed and removed by robotics, and all the work that we do in the target service bay is by robotic manipulators. So here you can see an image of one of the targets while it's being installed. Here are the manipulator arms coming down. Another thing we installed in the target service bay was an overflow tank shown here on the right, so that we could handle the high flow gas injection and not overflow the mercury. Yes, question?
Is this static mercury or flowing mercury?
It's flowing.
That's what I thought.
Yeah. Yeah, it's flowing. And then the helium system itself for injecting into the target, we had to do work on that. This is just one image of part of the helium recirculation system. In the past, we had a once-through system and the helium was being vented. Now we have a recirculation system so that we're not wasting the helium. When the protons strike the mercury, there are a lot of isotopes created, some of them rather unpleasant. And so we have a mercury off-gas treatment system that basically scrubs whatever's coming off of the mercury and prevents it from going to the atmosphere. And so we did quite a few upgrades there. These are molecular sieves that are installed in the facility. There's an iodine abatement system, and there are some other elements to that as well, just to make sure that we don't put out anything into the atmosphere. One other aspect of the target systems work was a ortho-para conversion catalyst that we installed on the hydrogen moderator. So when the neutrons come off the target, they're traveling too fast. They have too much energy. And we have to slow them down with moderators. We have moderators that are liquid hydrogen and water, two separate types of moderators. For the hydrogen moderator, the hydrogen is cooled to about 20 Kelvin. And the hydrogen exists in a couple states, ortho and para, as it relates to the spin states of the hydrogen. And what we want is para hydrogen because it has a smaller cross section and allows the neutrons to get moderated and out of the moderator and down to the beam lines. So that was part of the upgrade, and that is working very well. We had to develop the vessel, tie it into the refrigerator, develop diagnostics so we can measure what we have. So that.
How do you select para-hydrogen?
Well, we pass the hydrogen through a catalyst, which is full of essentially rust particles, iron oxide, and that catalyzes the hydrogen and converts it to para. That would happen naturally over a longer period of time, but we want it to happen immediately when we turn on the hydrogen loop. And so it's working great, and we're looking forward to seeing what the Neutron scientists have to say about it, how they utilize that in their instruments. So our timeline for the project is shown here. We started back in late 16, possibly in 2017. First, we had a mission need for both PPU and STS that was approved in 2009. And it took us some years to improve the facility performance until the Department of Energy was willing to actually give us the go-ahead on these upgrades. So in 2017, we completed the conceptual design. 2018 and 19, we completed some long lead procurements for mature technology. That is, we were duplicating equipment that we were already operating, cryo modules, the radiofrequency systems. And so we were able to get money in advance to get that work started. Then in 2020, we baselined the cost and schedule of the project. Final design was nearly complete at that point in time. But since then, we've been carrying out the project construction in 21 through 24. And we anticipate closing out the project next year. By this time, if everything goes well, we should be finished. But we do have some things we have to demonstrate before then. We have what are known as key performance parameters that we have to achieve. The things that we're obligated to achieve are the threshold key performance parameters, but we have objective parameters that we have installed all the equipment we need to meet those eventually, but that'll take a little bit of time. So today we're running at 1.7 megawatts at 1.3 GeV. I'll show you an image of that a bit later. We basically demonstrated beam power on target, beam energy, and stored intensity in the ring. One that's hanging out there is target lifetime. We have to run a single target at 1.7 megawatts for 1,250 hours and demonstrate that it can survive. And so we should have that demonstration complete in September. And then we'll be able to move towards having our final project review, CD4 project completion review that will be, it's already scheduled for next January. So status is given here. We completed a long outage in April that started last August and ran into the end of April. Installed all of our equipment, tested it all. We had an accelerator readiness review in May with external reviewers to make sure that we were ready to begin commissioning and routine operations. That's a big deal. We then had to get a letter from the Oak Ridge site office saying proceed. We got that in early June. We started beam commissioning, and we are planning to resume Neutron production for the user program later this week. We'll do the target lifetime demonstration, prepare project closeout documentation, and then we'll have our final review in January. And then there's a ramp up plan to increase the beam power to 2 megawatts and to increase the user hours over the next few years. Here's a snapshot from the control room that I made yesterday. Running at 1.7 megawatts, 1.3 GeV. Turning a machine like this on after an outage, any outage, but especially a long outage where you've made a lot of changes, is challenging. And it's gone very well, better than we might have hoped for. And that again is testament to a good team that's been supporting and working on this project. I mentioned a ramp up plan over the next few years. We're basically here at the beginning of this green bar. The green bars show beam power on target. So we're gonna run at 1.7 megawatts for a while and do that target lifetime demonstration. The blue line indicates the number of hours that we're committed to providing for the user program. So of course, in the recent past, we've not had very many hours, but our plan is to increase from 4,000 up to 5,000 hours per year for the user program. And that's not easy because things happen that cause downtime. There are equipment failures we have to deal with, but that's our goal. So by FY27, we plan to be running 5,000 hours a year at 2 megawatts on the first target station. And that's pretty exciting. I do want to mention though that, there's more to neutrons than what we're doing at SNS and PPU. We have a 3-source strategy at ORNL for neutron science. At SNS, we have the first target station, which is operating now. We have HIFER, which is operating now and has been for many, many years. And in the future, we're going to have the second target station. And with these 3 neutron sources, we are really going to be a leading neutron science facility worldwide. And you could argue we already are. Just a few slides about second target station. You can see where it's going to be sited here, adjacent to the existing first target station. It is optimized for cold neutrons and will be world leading in terms of peak brightness of the neutron beams, provides new capabilities for science, and it will be complete in the 30s. First science is due in 32 or 33. A little bit about the technology on this slide. We have the accelerator components, which basically transport beam from the existing ring to target beam line to the second target station. And we need to be able to operate both target stations simultaneously or independent of each other. The target itself is very different from what we have at SNS. It's a solid rotating water-cooled tungsten target. The image of that is shown here on the left. Has many pie-shaped wedges of tungsten. That's the target material. There are going to be instruments up to 20 eventually. 8 instruments are included in the project scope. Conventional facilities is a big deal in terms of the cost to the project. Building that new target hall is quite expensive. And then there are controls that are needed across the project. So what I wanted to show here is that the project has been divided into 3 sub-projects. And at the bottom of the page, you can see how those sub-projects fall in time. First one, sub-project 1, is for conventional facilities. And we're hoping to get that started early next year. There's going to be a review for CD3A, long lead procurements, at the end of this year in November, I think. And then if that goes well, we should be able to get started on some conventional facilities work. We've got a huge mound of dirt where the second target station is going to be. We need to move that out of the way, start doing some infrastructure work so that we're ready to build the second target station hall. Sub-project 2 is instruments for the early science, which should be ready in 33. And then sub-project 3 is the final 5 instruments that brings us up to 8. And then there's room to expand to about 20 instruments over the lifetime of that facility. And that's all I've got for you today. I hope it was interesting and useful. And if you have any questions, I'll be glad to take them.
What's the quantitative relationship between the increase in proton beam energy and the increase in the resulting neutron flux?
We'll get about 40% more neutrons. The scales directly with the power of the proton beam.
What about the intensity of the beam? The number per, rather than the energy of the beam, which is more important, the intensity of the beam or the energy of the beam?
It's the flux of neutrons, the neutrons per unit area per unit
No, I'm talking
time.
about the source, the driving.
The proton accelerator?
Yeah. Well, if you're producing a flux of neutrons, which is more important, the energy of the beam, proton beam, or the intensity of the proton beam?
Ah, I see.
To get to maximize the flux of neutrons.
Yeah,
Depends who you are, right?
What?
Depends what you're doing.
ultimately, you just want a flux of neutrons, right?
Not everybody.
Most everybody wants more neutrons.
The whole
But
idea,
they might
the whole
want,
idea.
but Ray, they might want a better beam shape. They might want crisper pulses. There's a lot of parameters other than just, well, neutron.
The increased energy does have an effect on the neutron production. But I think the power itself, the 2.8 megawatts or the 2 megawatts for FTS is really what dominates and creates the increased flux.
This is a related question to the ones just asked, emerging from the moderator in the present system. How monogetic are the neutrons and what is the divergence angle for the beam coming out?
So the neutrons come out in all directions, forward, backwards, up, down. And the moderators are the moderators are key to the instruments being able to usefully use the neutrons. We're a pulse neutron source, so we want pulses that are sharp in time so that we can do time of flight type measurements. Maybe didn't catch the last part of the question.
Just the question of how energetic are they after the scattering process?
Yeah. I'm sorry, I don't know the answer to that.
Yeah, a lot of that is not the accelerator systems, but the beam transport systems.
Yes, that's not.
The things that go downstream from the target.
Right.
What wavelength you have, whether you're just, again, talking to what Ray was asking, whether you're just looking at an experiment where the number of neutrons is the main thing that matters, whether as you're looking at a monoenergetic beam is what you need. These are research dependent questions, and each instrument has a beam transport system tailored to its need.
Yeah, but the spread of the energies of the neutrons when it gets to the experiment itself may influence the result of the experiment.
Yeah.
That's
Right, and that's in the beam transport system and the monochrometers and things like that.
You're presently using a mercury target and you're going to use a tungsten target. What is the relative advantage of going to that over mercury?
So we're going to be putting much less power on the second target station, only 700 kilowatts compared to 2 megawatts on the first target station. But I think that's the primary difference. You've got to get the heat out of the target, whatever it is. And for a high powered target like the first target station has, flowing mercury is ideal for that.
Do you get a higher neutron yield in mercury compared to tungsten?
I don't know for sure. Sorry.
You have concentrated on the energy of the beam here. Did you say much about pumping up the intensity? These things start out in negative ions. How did that get accomplished? And could that not have been done independent of this? Could you have done that earlier? You just need more protons.
So we've done a lot of work over the years to improve the performance of our ion source. It's at the beginning of the LINAC, both in terms of reliability and the current, the H minus beam that can be extracted from that. Yeah, and that's part of amping up the power capability of the LINAC.
But that's sort of independent of the energy part.
Yes,
Yeah.
correct. Dave?
Yeah, so back when they were delving into the target damage and cavitation to figure that out, they learned quite a bit about the dynamics of that. And I was wondering how the target's gonna put up with, the first target will put up with 3 pulses out of 4 because it's gonna go without being 1 cycle out of 4. And that's gotta cause some vibration.
So that is a concern for the future. and may require some more development work. Those pulses will be more, there'll be more charge per pulse hitting the target so that we can maintain a 2 megawatt power level with a lower duty factor. So that's work for the future. Beyond the scope of PPU.
Okay.
This is a housewife question. I would like to know where this all is located here in Oak Ridge. Is it directly at ORNL area?
It's at ORNL, the X10 site. And if you go into ORNL on Bethel Valley Road, it's first stoplight that goes, and you go up the hill on the Chestnut Ridge. Yeah.
You're not allowed in there.
When we started building in 1999, that was a tree-covered ridge, Chestnut Ridge. And over some years, we transformed it into what it is today.
Another thing is you mentioned a lot of I can't think of the name of that. There is fear in Oak Ridge about contamination through, help me,
Radioactive.
no, not radioactive, just uranium, no,
Mercury?
the stuff that you said you use an awful lot of.
Mercury.
No,
So the mercury is contained very well at the facility. We don't lose any mercury, but there are isotopes that are produced by the proton beam striking the mercury. So there's an off gas that contains hazardous materials, hazardous gases. And we capture those in a mercury off gas treatment system so that they don't go out the smokestack and into the atmosphere.
so none of that will run into the rivers then.
No, there's nothing running into the river. I mean, we operate under pretty strict regulations. I mean, we can't put anything into the river like might have been done in the days past.
Does it actually vaporize the mercury? I mean, boiling off mercury as well?
Probably, I'm not exactly sure. There's certainly a vapor that's generated.
Are those products of neutron activation of the mercury?
I'm not sure how to answer that. It's the interaction of the proton beam, it's the power deposition from the proton beam into the mercury. So
Okay, so
it's
from
not
the
just
proton
neutrons
beam.
coming off, it's other things, actinides and the like.
Want to know a little bit more about where that mercury came from?
Sure.
So there was a process at White Cloud and they were separating isotopes of lithium. And it was based on mercury, and I don't understand the chemistry. But that's what it's being used in buildings at White Cloud. A lot of it got away and got into the creek. But we were able, SNS was able to get what they needed out of that stuff.
And that mercury will last as long as the facility is running. We don't need to, we don't replenish the mercury. The mercury will last the life of the facility.
But that mercury has a history.
We also use heavy water in our moderators. And heavy water is a little bit hard to come by.
Yeah.
Yeah, the mercury is mercury, never mind.
It's mercury.
There must be some at the bottom of the fjord in Norway.
I might remark that when I was young, I worked in Beta 3 at Y12 and also Alpha 2. And the California, some of them were still running, and they used mercury diffusion pumps to pump the vacuum. And there were big ones. The diameter of the pump was on the order of 2 feet, and they were 6 feet high. And so the amount of mercury that was available in the Manhattan Project was huge. And there were famous leaks, particularly in Beta 3, when it flooded down the stairs and into the ground underneath the building. And probably we still have the historic record of that in the creek, but that's really the true story of why there was so much mercury here. And they continue to use those pumps until improved vacuum pumps are available using other things.
Did those pumps release any vapor into the rooms where they were operated?
Good question. There were a lot of survivors of the Manhattan Project, so I don't think it was
Just a lot of blackened teeth.
Yeah. I'm thinking of oil diffusion pumps, and then you can certainly smell them when they're in operation.
Right.
At one time, there was concern that the diamond stripper foil would burn up at the higher power. So that problem's been solved.
That problem's been solved. The diamond foils are fabricated next door at the Center for Nanophase Materials. And in the early years, we had trouble with the diamond foils curling up and breaking, and that problem's been put to rest. We've done experiments in the lab showing that they can take much, much more power than we're going to be putting onto them.
Because they were making radiant pools and things like that, so say curling was the biggest problem they were having. Before they made them at SNS, they made them in chemistry.
And what's the target thickness of those films?
The diamond films?
Yeah.
It's,
It can't be too thick.
no, it's probably on the order of 20 to 30 thousandths of an inch. I don't know exactly. And they have to be structurally sound, but they also need to be thin. And we handle them very carefully. Recently, we were doing some work in that section. And in backfilling and evacuating beamline, they have to go very slowly so as to not disturb the foils with the rushing air.
So you have an array of these that you can put in there when they burn up?
We have something that looks kind of like a chainsaw, and hanging off the chain
Okay.
are a number of the diamond stripping foils, and you can rotate new ones into place as needed.
I've got an English major question. What is the importance and role of superconducting magnets and radio waves to the success of the operation of the SNS?
So we don't use superconducting magnets, except there are one or two instruments that have some superconducting magnets for doing experiments on samples in high magnetic fields. The accelerator uses normal conducting magnets, but it uses the superconducting RF cavities. So the advantage there is that the superconducting cavities have a large aperture. And we're not about making a really small beam at SNS like you would in a collider. We just want to get the beam to the target, and when it hits the target, it's fairly large. We want a uniform distribution so we don't stress the target by putting pencil beams onto it. Superconducting cavities don't dissipate any power. The RF power all goes into accelerating particle beam. And that's one of the big advantages.
So is it the radio waves are doing that, or?
The radio waves are accelerating the particle beam. We set up oscillating electromagnetic fields in the cavities, and the beam arrival time is phased against the radio frequency signal such that when a bunch of beams comes into the target, it sees a kick from the electric fields. There's a lot of flexibility in having a superconducting LINAC. As I said, each cavity is controlled by its own RF system. We can have cavities go offline because of a technical problem in the RF system, and we can keep running. We have to rephase the downstream cavities. You can't do that with a copper LINAC. If in the couple cavity LINAC we have a failure, then we're down until we fix it. We can also remove individual crown modules from service if we have to. We can bring them out of the tunnel, do work on them across the street. We can replace them with a spare, or we can replace them with a beam pipe and just lose a little bit of energy. So it's provided a lot of operational flexibility for us. Yes, sir.
Did I understand correctly, your last response is that the energy conversion process from the RF to the particle beam is 100% efficient?
There's no heating, very little heating. You're not losing you're not heating the copper like you would in a copper cavity. Yeah, it's essentially a lossless conversion. Yes.
So, this stuff took space in an existing tunnel. Was this thought of in the original design? Were you removing and replacing modules, or was there space available?
So originally, we were going to build a copper linac, the entire length of the SNS. And that was going to use all the existing tunnel space. And then fairly late in the game, we switched to superconducting. And that gave us that empty space that we could then use for an upgrade in the future. So it was a fortunate situation. Yes.
What's the energy input to operate this facility at whatever, you know?
We use about 30 megawatts of AC power to operate the SNS, the whole site.
Okay.
And that's, I don't know, the whole lab, down the
That's
hill,
not
other
a
part
lot.
of the lab uses 50 or 60 megawatts probably.
Yeah,
Yeah.
computers.
Supercomputer itself
Yeah,
uses a
yeah,
lot.
yeah. 30 megawatts is not huge for a big facility.
Wow.
So, yeah,
Not
it is.
small
but-
either.
Oh, no, but, yeah. Consider,
Our electric
it's
bill is on
not,
the order of $1 million a month.
it's not the output of an entire power plant, example, generating plant.
Well, do neutrons induce radiation damage? I don't know what it is. I mean, does it do anything in
Yeah.
materials?
Yeah.
I mean, there's a lot of neutrons there.
Yeah, although the number of neutrons that actually make it to the instrument is quite small compared to the number of neutrons that comes off the target. It's not a very efficient process. But yeah, neutrons will cause damage.
What's the international competition?
So the Europeans are building the European spallation source in Lund in Sweden. And that's still, they're doing commissioning activities now, and they're maybe a year off from first beam on target. That is only a linac. So they've got a linac that's going to run at, I think they're going to produce 5 megawatts of proton beam that they'll put onto a rotating solid target. And in some areas, they will surpass our capabilities with the SNS. But they've got a ways to go yet to actually demonstrate that. There's a Chinese spallation neutron source in operation. I don't know its parameters off the top of my head. And then there's the J-Park facility in Japan that has a similar facility. And then there's the ISIS facility in the UK that is doing neutron science based on the spallation neutron source. Otherwise, you have a variety of reactors around the world that are used to produce neutrons. ILL in Grenoble is perhaps best known in Europe. IFER is, of course, the other one that we have here.
What science objectives can be met or will be met in the second target station that aren't being met now? What kind of science will be done there, assuming that it goes according to plan?
So it produces what we call cold neutrons. Neutrons that have a different energy or wavelength. And that is useful for different types of experiments. And I'm sorry, I'm
That's
not an
okay.
expert in that area,
That's okay.
but it is complementary to what we can do with the spallation neutron source now.
Longer wavelength.
Smaller sample, more extreme conditions.
It's a comment in the chat from my colleague Bernie Reamer.
Okay.
What does he say? Bernie says there is no boiling of the mercury under normal operation nor accident scenarios. The mercury at SNS was obtained from Y12, thoroughly characterized for isotopes and impurities before acceptance at SNS. He says components that suffer high amounts of radiation damage are designed to be replaceable. And Other important spallation neutron sources are in Japan, JPARC, ISIS in the UK, and Sign Q in Switzerland. I forgot that one. And he says, hi, Mark. Bernie's in Atlanta, unfortunately, so he couldn't be with us, but he was a very strong contributor to PPU up to his retirement a year or two back. And there have been many other people who've come and gone, retired or moved on to other career positions, and they've all contributed, and we appreciate that.
It's time to thank you. Thank you for the presentation.
You're welcome. You didn't give me too much time to prepare.
Yeah, thank you for doing it at the last minute. Yeah, that's.
You're welcome.
The timing was right, though.
You might think about, HIFER upgrades as a potential future conversation.
Okay.
There's a lot going on there.
Is there a funded project there?
So the pressure vessel replacement is a project. I don't know how strong the funding is yet, but it's underway. And then they're doing other upgrades to HIFER, the beryllium reflector, and some instruments and beam lines. And that's being done under operations funding.
So they're comparatively low level.
They're in the early stages of developing those upgrades. And the second target station is coming along, but it's got a ways to go.
Second target, second guide ball.
Pardon me?
Were you talking about HIFER?
HIFER, yeah.
Well,
Second
HIFER
guide ball.
first and then second target station.
And
later
then
might come.
SNS.
Yeah.